Good morning. I'm James Kinsman, Technical Director and CTO at Overview. I'd like to talk today about the paradigm for sensor motion, how it's changing, and what that means for agility and accuracy in smart sensors. What does that actually mean? Well, the paradigm is an example or pattern. How is something operating? Sensors, obviously, are a device detecting or measuring physical properties. And motion is the action or process of moving or being moved. The majority of sensors deployed in the world are deployed into security services. Agility and accuracy of those are based on human operation, spatial awareness, and the lowest common denominator. So the slide you can see here has some examples of some common sensor systems that are in operation. And the sort of scenario that it might be used in this particular picture is a picture of Hackney CCTV control center. How are they used? Well, they're used in what we term the effect loop. So we start in the observe criteria. Our friend in the control center there is watching traffic or a town center. Every time he's observing, he then moves on to assess. So he's looking at the condition of the traffic, he's looking at the number of people in the town centre. And then based on that, he might trigger an effect. So if he's watching that town centre, he sees an altercation, then he's going to vector in some security personnel, that may be police or local enforcement. There are somewhere between 4 to 6 million CCTV cameras deployed in the UK. And in order to operate those, there are just under 500,000 CCTV operators. So that means on an average, there are about 10 cameras per operator, but that doesn't account for downtime, shift patterns, and otherwise. The Hackney CCTV control center that you can see there has just shy of 3,000 CCTV cameras deployed into it, and that's being operated by a team of 10 operators. So the effectiveness of our CCTV operators and the cognitive burden is becoming a massive impact. So how can we improve this? Moving to a smart sensor adds a machine learning capability between the sensor and the operator. That gives us the ability to increase our output efficiency, and that might be through a fully autonomous system or a semi-autonomous system where it's using cues and machine metadata to help ease the cognitive burden of that operator. It also makes sure that we're taking the human out of harm's way. We are having people deployed at a safe distance rather than out directly in the field. So what does smart sensors and digitization mean for the sensor motion platform? I'd like to take a little time to do an exercise on your observation. I'm about to show you a still image, and I'd like you to see what you can determine from the very short amount of observation that I'm going to give you. So 3, 2, 1. Did you manage to determine anything about that picture? You might have noticed that it was something to do with a sport. The image there was on screen for 2 frames. So let's try an exercise that's slightly more realistic for an operator. I have a short video here. It's got 2 teams, white and black. When I hit play, I'd like you to try and count the number of passes that the white team makes to each other. Don't need to count the black. Correct answer there was 13. Were you right? Did you notice anything else? Now let's see how a AI or machine learning model would do. Firstly, with just a single frame. Now what we can see here is that the AI is detecting people, it's detecting the balls, it can count the passes. It also detects a person in a gorilla suit, and I don't know whether anybody noticed it. It's just coming on screen from the right here, picking that up and detecting that there's an additional person in a costume. Now this is a contrived example. This was an experiment done by MIT nearly 15 years ago, and they found that 50% of people watching the video missed the gorilla. The AI assesses frame by frame, and it can keep track of more than one context, more than one item. So we're tracking the passes, the characters, and the black team as well. Machine learning and AI is not there to replace operators, it's there to reduce the cognitive burden on the operators and ensure that they are more effective in their day-to-day job. So AI enables us to close the effect loop quicker, get to that action and effect at the end of that loop. This means our system performance can increase, but what does that mean for the overall motion platform? We have to look at three areas: the motion requirements, motion capability, the control of the system, and also both the physical and sensor architecture. So let's start with the motion. The quickest route from A to B is a straight line. We know this. Physics, however, isn't ideal. You have to start at 0 speed. You have to speed up, travel at our maximum speed, and then slow down. Now, what you see here is both the position that's trying to achieve and the velocity curve to achieve that. Now, as we increase our velocity, the time at the top of that curve is getting less and less. If you just pull that up on the same acceleration, you're almost going to hit 0 time at your maximum velocity. So the acceleration of your system becomes a very, very important factor. Not only acceleration, but also jerk, the rate of change of acceleration. In a real world example, most vehicles on the road today can reach over 100 miles an hour. The top speed between a Tesla or a Ford Fiesta is very, very similar. However, which one would you rate in a drag race? Acceleration is absolutely key. Sensors, we always stipulate the maximum angular velocity that a sensor can achieve, but very rarely do we start looking at the acceleration and how quickly can you get to that maximum velocity. Can you use it all of the time? We also need to be able to stop quickly at the other end of the curve. It's not enough to just get to maximum velocity as quickly as possible, but you have to be able to stop exactly where you were aiming to. The position is very important, and we'll talk about that as we go through. So in addition to our total speed and acceleration, we also need to look at our control latency. Data from sensor payloads is being updated hundreds of times a second. Increasingly, we're seeing the likes of event cameras, high frame rate cameras. And the motion platform has to be able to respond to this. So taking another look at our S-curve motion profile, we need to be able to account for the interruption of the motion profile. Most modern day servo controllers use a trajectory generator, which pre-computes the motion profile for a move. So after a position demand, the velocity and inherently the acceleration demands are calculated with the knowledge of the physical system. How is it going to respond? So we receive a position demand and we calculate that velocity. We move to that velocity using that high acceleration and then run at our velocity until we reach the position we were aiming to get to. Now we then start decelerating to end up coming to a stop. But what happens if in that time we end up with a new target location? So we have to be able to not only generate that trajectory, but also to interrupt it. We have to be able to continually update and parse our final position. And we have to be able to do that quickly. If we have to take a long time to recompute that trajectory, then we're starting to overshoot and then have to come back round. So the control latency is a very important factor in this. Now, moving on to look at our physical architecture and our systems architecture. Payloads are getting more sophisticated. Sensor systems that were traditionally visual only are now increasingly multimodal. That may be lidar, that may be thermal, a whole number of extra capabilities that are becoming very, very affordable. That means we need more drive torque. We need the ability to move heavier payloads and still at those speeds that are increasing. Our sensor range is increasing. That means that our positional accuracy is becoming very, very important. If you have a fraction of a degree in a nice wide angle scenario, that's not a problem. But if your total field of view is only a degree, then moving half a degree in positional accuracy is half of the picture. Becomes very, very important. We also need to consider the sensor bandwidth demands. We are getting multiple gigabits of sensor data into AI processors. So we have to look at the transmission format, and we have to look at how we get that data into the edge computing capability as quickly as possible. Now, traditional architecture has the processing and encoder in the head. That is the most optimal for absolute low latency encoding. However, the challenge with that comes to the motion performance of that. As our AI processors and our encoders get bigger, they get more powerful and more capable, we're pushing heat, we're pushing mass up into the head of the system. And that affects the fundamental kinematics. If something is heavier, then it is harder to get it moving. You either need more power in the drive or you can go slower. So smart sensor architectures are now starting to look at a split system where you have the sensor in the head and then bring that in raw data unencoded down into the base and make sure that your AI coprocessor is in the base of the unit rather than up in the motion head. Now that has significant implications on the complexity of the wiring harnesses, complexity of slip rings if it's a continual rotation system, because the bandwidth that you're passing over these drives and interfaces is no longer a 4 to 10 megabit video image, it's a multi-gigabit raw sensor feed. So overall, how's the paradigm changed? What's happening in the industry at the moment? We are using machine learning to close the event loop quicker and more efficiently. That means that we can take advantage of higher agility. Machine speed, low latency processing means we have to take advantage of increasingly low latency control mechanisms. And our situational awareness is enhanced by companion data. We're putting additional metadata information in front of the operator. Accuracy is absolutely critical. Our pointing accuracy is increasing to multiple kilometers, tens of kilometers out, and our data is being used for geolocation. So if we have that metadata information, it's not enough to say that there's a person, we have to say where that person is. And control latency, again, very, very important. We have to be able to respond to those latency inputs at machine speed because the machine is making decisions tens to hundreds of times a second, and that's really, really important. Thank you very much for listening. I hope this was very interesting. If you have more questions or you'd like to learn more, then do please reach out to us at the team and you can find more information on this and the contact details at www.overview.co.uk. Thank you very much.